tension pulling it in the positive direction. So when I look at Newton's second law again, it's still the net force divided by the mass. But look, I already know how much it's accelerating. I found that over here. So I can say 5 meters per second squared equals the net force. What's the net force based on my free body diagram?
10 plus t. No, t minus 10.
T minus 10. T is in the positive direction, 10 is in the negative direction, so it's T minus 10 newtons. And the mass, of course, is just the 1 kilogram. Whoops. 1 kilogram.
You can cross out the mass.
Right, so I'll multiply both sides by 1 kilogram, and I end up with 5 newtons. What minus 10 newtons gives me 5 newtons? 15 newtons. Okay. Here we go. All I'm doing here is I'm adding 10 newtons to both sides, by the way. And 15 newtons. Beautiful. Now we want to know the distance. Remember, your kinematic stuff is still fair game on the test. It wants to know how far it is moved, each mass is moved, if they both start from rest. What does that word, start from rest, or that phrase mean? Okay, so VO equals 0 meters per second. Okay. And if I want to know how far, that's my displacement. I'm calling it y because it's moving up and down. And so that's just VO times t plus 1/2 AT squared. Of course, that's gone, right? 0 times anything is 0. And then I just have to substitute 5 meters per second squared for acceleration. And 1 second, oh, is it 1 second? Yeah, 1 second. And I'll square that for time. That'll give me 2.5 meters. I realize I'm going through this really quickly. So if there's a point where you got lost or get lost, please pause and say, should you back up? Yeah, Lamar.
Yeah, we're on set T minus 10.
Okay, so right here, and so I can get T all by itself. So I multiply both sides by 1 kilogram.
Yeah, how did you cross out the 1 kilogram?
Oh, yeah, I should have done it like this. So before I had this plus 10 over here, I basically did this. It said 1 kilogram multiplied by the right side and 1 kilogram multiplied by the left side. It'd give me 5 newtons here, and it would just be T minus 10 over here. Any other questions on this particular problem?
So why do you choose that particular acceleration formula to the right?
This? Oh.
Yeah.
I picked this, guys, because I didn't know how fast it was going 1 second later. And so I needed a formula that had the information I knew. I knew the initial velocity and the acceleration. I wanted to find the displacement, so I chose that one.
Oh. Alright.
That's in your formula sheet. So you want to make sure you're familiar with it. Alright, guys. The student's standing on a scale on an elevator. What does your scale measure? The normal force. Thank you. It doesn't measure your weight at all. It just tells you the normal force. Now on a flat surface, that will also be equal to your weight. So let's just bear that in mind. The guy, when it's not moving, the scale reads 900 newtons. So what do we know about the forces acting on him? Yeah, this 900 newtons then actually is his weight. Right? If the scale reads that when there's no acceleration, there's 900 newtons pushing down. When the elevator starts moving up, the scale reads 1,000.
Can you move it down? It's like an
Oh, I'm sorry, guys. Yeah. When it starts moving up, the scale jumps up to 1,000 newtons. Did he gain 100 newtons in weight?
No.
No. What's happening there? Yeah. In order to accelerate upwards, you need a net force upwards, so there had to be more force pushing up than pushing down. So again, the scale is going to read the normal force, and that would be the normal force. We want to know the acceleration of the elevator. Well, the acceleration is just net force divided by mass. Well, the net force is easy to find, right? That's just 1,000 newtons minus 900 newtons. But what's his mass? It didn't give us his mass. 90, yeah, right. If he weighs 900 newtons, he has a mass of 90 kilograms. And we would just divide weight by g. Okay? So 90 kg. And so he's accelerating 1.11 meters per second squared. We all right there?
That's all we had to do.
Wait, what?
That's all we had to do. How did you divide it by 9?
Because it's net force divided by mass. And we just figured his mass was 90 kilograms. Right? 90 kilograms weighs 900 kilograms.
I didn't know how to do that.
It's this man. It'll tell you that.
Okay.
Mindy asked a good question on the test. Will we be using 9.8 or 10? The answer is I don't know. When I print them out, it should say one or the other.
Oh,
Yeah. Okay. Let's look at this elevator car, right? We've changed an AP Physics 1, AP Physics B question to an AP Physics 1. So there's some questions that are a little wonky, but this one's okay. What forces act on a 400 kilogram elevator car?
It's not the.
Oh, this one. We already did the helicopter problem on Friday.
No, we didn't. You only had it in this packet, and we were doing the.
But we did that as part of the practice test.
yeah, but we'll talk about it. We never got to
We never got to it, my goodness. That's a shame, because it's a good question. So let's look at it. Sorry about that. Thank you. I love being supported like that. All right. We've got a helicopter lifting a package. Here's the package, and here's the helicopter. We want to label the forces that are acting on the helicopter. On the package. Thank you. Okay.
Brownie points.
No, I got that. But like, no, but it looks like a man standing on a block.
It does. So those are the cables. Okay, let's focus on what's important. What forces are acting on that particular package?
Gravity.
Should we focus on this dot in particular?
So that's F sub G down. Which one's bigger? It's accelerating upward.
Yeah. Oh, so. Yeah, but the helicopter.
So the tension's got to be bigger.
Yeah.
Okay. And it says us to neglect air resistance, so we're done with the forces. That's it. Okay. Now we want to determine the tension in the rope. That should be pretty darn simple, right? What do we need to know to figure out that force? We need to know acceleration, and guess what? We're getting it. Woo. That's acceleration, right? We also know the mass, right? So acceleration is just net force divided by mass, right? And we said the acceleration is 5.2 meters per second squared. Based on our free body diagram, what is the tension? I'm sorry, what is the net force?
T minus 70.
Yeah. And by the way, what is F sub G?
700
newtons. Good. Okay, and then mass, of course, is just our 70 kilograms. Okay, let's solve this bad boy, right? Multiply both sides by 70 kilograms. What is that, 364?
Yeah, sure.
364 newtons equals T minus 700 newtons. We're going to add 700 newtons to both sides. And so our tension is 1064 newtons. Yay! Pretty straightforward, right? You got to apply Newton's second law. But the free body diagram was the key. If you don't have a free body diagram, guys, you're not going to be able to get the tension. Okay.
Wait, why?
Because you're not going to know to do this. Find the net force.
Oh.
Right? You might just say force equals mass times acceleration. Take the mass times acceleration again.
This is good. On the test, what you care if like the arrows were bigger or smaller?
Not really.
All you hear about the numbers.
Because we're gonna figure out the numbers later. All right, guys. I is a why is it I don't know. But it's a conceptual question. What happens is what happens is the rope is cut. Yeah, that is sad. But the pilot wants to keep accelerating at 5.2 meters per second squared. What does he have to do to maintain that level of acceleration? Yeah, decrease the upward thrust, right? Because now, if you look at the helicopter had its own weight, and then it had the weight of the package. I'll just call that FG1 and FG2. And then it had the thrust upwards. Sorry. Okay. And now if this one is gone, right, when the package gets dropped, when the rope gets cut, he's got to decrease his thrust in order to maintain the same acceleration. All right. Part C, though, is yes.
Oh, so how many conceptual questions? I don't know if you have any sense on.
Every one of them has a conceptual element to it. Excuse me, guys. Let's focus here. The C is probably the toughest question on this whole pack. You've got a helicopter, right? And the helicopter is accelerating upwards at a certain rate. When that rope gets cut, the package is accelerating downwards. I'm going to call those acceleration 1 and acceleration 2. We want to know about the distance between the two. So you can make it long or short, basically. You can figure out, based on this acceleration and the initial velocity of the helicopter, where it's going to be 2 seconds later. You can figure out, with this acceleration and this initial velocity, where this is going to be 2 seconds later, and then add those two distances. That's one way to go. Yeah, no.
Will both of their initial velocities be 30 meters per second?
What do you think?
Yeah. That's what I thought, but just in case that wasn't true, I had another one where.
Okay, so your gut was telling you the right thing, right? If you're moving and something is in your hand, right, that thing is moving at the same speed that you're moving. Okay? And so they both have an initial velocity of 30 meters per second squared. I'm sorry, 30 meters per second. However, we could make this a lot quicker. And we can look at the relative acceleration between the two of them. This one's moving and accelerating at 5.2 meters per second squared. What about this one? What's this acceleration? 9.8 meters per second squared. Relative to one another, how fast are they accelerating? 15, yeah. It's 5.2 meters per second squared plus 9.8 meters per second squared. And so that's 15 meters per second squared. Just like if you were in a car going 5 miles per hour this way and somebody was going 10 miles per hour that way, relative to one another, you're getting further apart by 15 meters per second, right? You just add those two speeds. Same thing with the acceleration. Relative to one another, what is their initial velocity? Yeah, they have the same velocity, so relative to one another, at the beginning, 0. Just like if we got Tyler and Michelle in a car together, and they're both going at 30 meters per second, relative to one another, they're going 0. Okay? So if we just use these two things, we can find the distance after 2 seconds just by applying this formula. VOT plus 1/2 AT squared. Okay? And we'll use the relative. That will make it a lot quicker than figuring out where this is going to be and where this is going to be.
What is that? What was that?
Oh, relative to one another, they have no initial velocity. Yeah. Oh, yes, it should be. Okay. All right, I'm not going to plug the numbers in because I want to make sure we cover the problemas. There we go.